When examining the pharmacokinetics and bioavailability of niacin, nicotinic acid, versus nicotinamide riboside, NR, and nicotinamide mononucleotide, NMN, it becomes increasingly clear that the simplicity of niacin's metabolic pathway may, in many contexts, confer a distinct advantage. Despite the molecular sophistication and marketing appeal of NR and NMN, their added biochemical complexity introduces multiple layers of uncertainty, both in terms of cellular uptake and systemic conversion. By contrast, niacin's straightforward entry into NAD+ biosynthesis via the Price-Handler pathway can translate to reliable and efficient elevation of NAD+ levels, especially in metabolically active tissues such as the liver and kidneys. This metabolic economy, coupled with niacin's decades-long track record of therapeutic use, underlines the value of simplicity in nutritional pharmacology. Oral niacin is well absorbed in the small intestine, with bioavailability exceeding 70% in most formulations. Once absorbed, it undergoes a relatively linear transformation into NAD+ through a defined and well-characterized route. The key enzyme, nicotinic acid phosphorybosyltransferase transferase, NAPRT, is widely expressed in liver, kidney, spleen, and immune cells, ensuring that niacin's journey to NAD+ production is both predictable and robust. This consistency allows for efficient systemic replenishment of NAD+ pools with minimal intermediate steps or metabolic detours. In contrast, NR and NMN introduce significant variability due to their more complex metabolic fates and cellular transport dependencies. NR is first converted into NMN by nicotinamide riboside kinases, NRKs, then into NAD+ via NMNAT enzymes. NMN, despite being closer to NAD+ in structure, may not be directly transported into most cells as once assumed. Many studies now indicate that extracellular NMN is dephosphorylated into NR before uptake, essentially rendering it functionally similar to NR at the cellular level. This indirect route makes NR and NMN more reliant on specific transporter expression, e.g., YNT and SLC12A8 systems, which are variable across tissues and species, leading to inconsistent outcomes in clinical contexts. The metabolic burden also differs. All three precursors eventually elevate NAD+, which in turn increases nicotinamide NEM levels, a byproduct that must be cleared via methylation. High doses of NR or NMN may contribute more heavily to the methylation load due to their rapid conversion and potential for overaccumulation of NEM. This can tax the methylation cycle and lead to secondary nutrient demands, particularly for methyl donors like folate, B12, and choline. Niacin, because it does not pass through the nicotinamide intermediate early in its conversion pathway, produces less immediate NEM and may distribute the metabolic load more evenly over time. Furthermore, niacin's activation of the GPR109A receptor induces beneficial signaling effects independent of NAD+ production, an added layer of utility that does not increase metabolic stress. Conversion efficiency is another point of divergence. Niacin's conversion to NAD+ is relatively lossless in tissues with high NAPRD expression, while NR and NMN may face conversion bottlenecks if NRK or NMNAT levels are limiting. While NR has shown success in raising NAD+ levels in blood and muscle tissue, the extent to which this translates into functional improvements is still under active investigation. Some trials have found only modest or variable increases in tissue NAD+ after NR supplementation, with unclear clinical implications. NMN, though effective in some rodent models, has shown mixed results in human trials, and its pharmacokinetics remain less clearly defined due to the possibility of extracellular degradation before uptake. Moreover, niacin's systemic effects are not just byproducts of NAD+ synthesis, but are themselves part of its therapeutic signature. Its impact on lipid metabolism, inflammation, and vascular tone, largely through GPR109A activation, has been repeatedly validated in clinical settings. These parallel mechanisms enhance the utility of niacin as a multi-target intervention, whereas NR and NMN remain narrowly focused on NAD+ replenishment without ancillary receptor-mediated effects. Finally, simplicity supports compliance. Niacin is inexpensive, widely available, and extensively studied in human populations. Though the flushing effect remains a drawback for some individuals, this side effect is dose-dependent, manageable with slow-release formulations, and, importantly, a biomarker of pharmacologic engagement. In contrast, NR and NMN lack such visible markers of efficacy, and long-term data on safety, optimal dosing, and off-target effects are still being generated. In summary, while NR and NMN offer targeted strategies to support cellular NAD+ levels, particularly in tissues with high salvage pathway activity, their dependence on multiple conversion steps and transport mechanisms can introduce inefficiencies and unpredictability. Niacin, with its direct, efficient, and well-characterized metabolic route, remains a metabolically economical and therapeutically versatile option. In a biological system where minimalism often leads to robustness, niacin simplicity may indeed be its greatest strength, especially for individuals seeking systemic NAD+ restoration with a trusted, efficient, and clinically proven molecule.